In this video, we're going to look at metal complexes. We're going to see how to name coordination compounds and then how to work out the number of d electrons that the metal has. A coordination compound contains a complex and any counterions that are needed to balance the charge of the complex. So here we have a coordination compound of cobalt. The square brackets tell us that the complex ion is the cobalt with 6 ammonia ligands. So we have cobalt 3+ with 6 neutral ammonia ligands, giving us a complex ion with a 3+ charge. We have a 3+ charge on the complex ion, and so we need 3 chloride counterions to balance the charge. So how do we go about naming these complexes? Well, let's do it in stages. Let's first think about the ligands. If it's a neutral ligand, we just use the normal chemical name. So pyridine stays as pyridine, cysteine is cysteine, etc. For historical reasons, there's some exceptions to this. Water has always been known as aqua when it's a ligand. Ammonia has always been known as amine with a double M. This needs amine to be the organic amines. We have anionic ligands, negatively charged ligands. We add an O as the suffix. So fluoride becomes fluorido. Chloride, when it's attached as a ligand, becomes chlorido. Bromide, when it's attached as a ligand, becomes bromido. Cyanide, cyanado. Hydroxide, hydroxido. So to indicate the number of ligands of any type, we add the appropriate Greek prefix like di or tri or tetra, etc. So if we have 2 chlorido ligands, we have dichlorido. If we have 6 amine ligands, we have hexamine. Notice that we need to be able to go backwards. We need to chop this up in order to work out exactly how many we've got. So the spelling is preserved. So although it may look ugly, we have tetraaqua, double A, and we have hexamine, we have double A again. If it's a polydentate ligand, we use bis, tris, or tetrakis, etc. If there's more than one ligand type in the complex, these are listed in alphabetical order. There's no space in between any of these things. It's just one long, very long word occasionally. Note the prefixes don't affect the order. So it's diamine, dichlorido, difluorido, because amine is before chlorido is before fluorido, A is before C is before F. Or we have triamine, dichlorido, fluorido, because A is before C is before F again. Okay, let's think about the metal now. If the complex is neutral or positively charged, the normal metal name is used. But if the complex is negatively charged, 8 is added to the metal name. So we have cobalt 8, zinc 8, if the cobalt or zinc is in a negatively charged complex. Again, history has given us things that people aren't going to give up. And so we don't have iron 8, we have ferrate. We don't have copper 8, we have cuprate. We don't have lead 8, we have plumbate. Because of history, we're not going to get rid of these words that have been used for hundreds and sometimes thousands of years. So we know how to do the ligands and we know how to do the metal. The metal is named after the ligands, and again there's no space between anything. The name of the complex ion is just one long word. We add the oxidation state of the metal in Roman numerals. So we have an iron 3+, then it's an iron 3, with 3 represented as III in the Roman. Manganese 7+ becomes manganese 7, or if we have a negatively charged complex, we have an 8. We have cobaltate 3 or cobaltate 2 to indicate the oxidation state of the cobalt. So we've named the complex ion. The counterions that are needed to balance the charge of the complex ion are named as separate words. And they're not numbered because we can work out how many counterions we need because we know the charge of the complex ion. If we've got cations that are needed to balance the charge, we put them before the complex ion in the name. So here we have potassium counterions. And so we have potassium hexacyanado cobaltate 3. But anions are named after the complex ion. So this cobalt complex has a chloride counterion. And so we have tetraamine dichlorido cobalt 3 chloride. Notice we have 2 chlorines attached to the cobalt. So we have dichlorido, and we have a chloride which is outside the complex, which is a counterion, which is chloride. There's a space between the cation and the complex ion in the first example, and there's a space between the anion complex ion and the chloride, the counterion, in the second example. This is how we know what's the cation and what's the anion. There's no space anywhere in the complex ion's name, but there's a space between the counter ion and the complex ion. Okay, that's it for naming. So we can now read and write the name or the formula of a coordination compound and work out what the complex ion is, work out what the ligands are, and hence work out what the charge on that transition metal is. We're talking about atoms. The first row of the transition metal are occupying the 4s orbitals and then the 3d orbitals. How do we know how many valence electrons a metal atom has? Well, we can get it straight from the periodic table. The group number tells us the number of valence electrons. Iron is in group 8, cobalt is in group 9, nickel is in group 10. An iron atom has 8, a cobalt atom has 9, and a nickel atom has 10 valence electrons. We're filling above the argon core. So the electronic configurations of all these atoms, we fill the 4s and then we start occupying the 3d. So we start off with potassium in group 1. We have one valence electron which goes into the 4s. Over scandium, since in group 3, we put 2 in the 4s, leaving 1 in the 3d. Manganese in group 7, we have 7 valence electrons, 2 in the 4s and then 5 in the 3d. Nickel in group 10, 10 valence electrons, we put 2 in the 4s, giving us 8 in the 3d. And lastly, zinc all the way over in group 12, 12 valence electrons. We filled up the 4s with 2 electrons, putting 8 in the 3d, which are also filled. In their complexes, the transition metals are cations. These are actually much more simple. In the cations, only the 3d are ever occupied. The 4s is always empty. The group number tells us how many valence electrons the atom would have. The oxidation number tells us how many that cation has lost. So the group number minus the oxidation number tells us how many electrons are left over, and these will fill the 3d only. So manganese is in group 7. Manganese 7 plus has lost 7 valence electrons. It's lost them all, and so it has a 3d 0 configuration. Whereas a manganese 2 plus, we have only 2 lost, and so we've got 5 left over, and these occupy only the 3d, 3d5. Nickel is in group 10, it's an oxidation number of plus 2, it's lost 2, it has 8 left over, 3d8. There's a nickel 3 plus, it's lost 3, and so it has 10 minus 3, 7 left over, 3d7. So from the formula or from the name, we can work out the oxidation number, and we can use this little trick in order to get us the 3d configuration very quickly. So in both these cobalt complexes we met earlier, we have in Roman numerals a 3, telling us the oxidation number of the cobalt was 3. Cobalt's over in group 9. Oxidation number 3 means it's got 6 valence electrons left, in which case the configuration is 3d6.